Okay, buddy, here's another one of those absolutely huge problem statements for us to practice in cogeneration. So let's look at it, walk through it step by step, and we'll figure it out. So in this case, I have steam. It's going to be supplied from a boiler to a high pressure turbine, okay, whose isentropic efficiency is 85%. Okay, so we've got one turbine, 85%. At conditions to be determined. Oh no. The steam is to leave the high pressure turbine as a saturated vapor. Okay, that gives me a quality and a pressure, nice. And the turbine is to produce 5.5 megawatts of power. Not too bad so far. Steam of the turbine exit is extracted at a rate of 1,000 kilograms per minute and routed to a process heater. The rest of the steam is supplied to a low pressure turbine whose isentropic efficiency is 80%. Low pressure turbine allows the steam to expand to 10 kilopascal pressure and produces 1.5 megawatts of power. Determine the temperature, pressure, and the flow rate of steam at the inlet of the high pressure turbine. Use the steam tables. Okay. So it looks like we've got a boiler. I'll just put a B for boiler. That is then flowing 100% into this high pressure turbine. Okay. After the high pressure turbine, it seems like it goes all the way through it. And let's see. And it is splitting at this point. So I have one that's going into a process heater. I'm just going to call that PH. And the other one that's going into a second turbine. And then after that, we would be having some pumps, which we're not going to worry about too much because it doesn't really matter for us too much. And this would be combined back into one fluid stream before going into my boiler. Okay, something along those lines. So we have a lot of work to do here. Now, while I drew this little diagram, that's mostly just so you can kind of see how it might be routed around, because I didn't give a good picture in this one. But the biggest thing for us is simply to draw the process. Now, this process diagram, you're like, wow, this doesn't look all that different. What about the cogeneration? The cogeneration isn't going to show up here, because the cogeneration is when I'm sending that excess heat, the heat that is leaving this cycle, I'm just sending it to a process heater. So we're not really going to see it here. Okay, so this is the point before the boiler. This is the point before the pump. This is the pump. I then put it through the boiler, gets heated up. It wasn't 100% efficient, so we have this line right here, which is me pretending it's efficient, then I correct it. And I go down again, pretending it's efficient, and I correct it. Things it told me that my saturated, my exit of my high pressure turbine was a saturated vapor. That's how I know that point right there is on that line. And it's always a superheated vapor after it comes out of the boiler. So we've got a lot of details here. What we're going to do is just going to take it one step at a time with what we know and go from there. So the place I know the easiest right now, I'm going to guess we're going to go with 0.4 first. That'd be the easiest one, I think. So I know everything about state 4. I know its pressure and I know its quality. And so that's enough. I can get it from that. So I'm going to go to my steam table. So I'm going to go to a pressure of 1.4 megapascals. I'm going to look up the enthalpy and the entropy. I know it's going to be the G1 because it is a saturated vapor. Okay, so I've got one enthalpy. I've got an entropy. That's all fine. And I can now use this entropy to find out other information. For example, I can use it to help me to find these points. And eventually I'm going to use it to help me find these points as well. There's all these things I can use to find it. So let's get state 5s from our steam tables. So we know that its entropy is going to be the same because the 5s is me pretending that this is an isentropic turbine. We'll then correct it afterwards by saying it's only 80% efficient. It's not 100% efficient. And so with that, let's go ahead and look it up. Now it told me that it was 10 kilopascals, which is great. So I know my pressure. I know this is saturated vapor. Sorry, it's a saturated mixture. And now I'm going to have to realize that, well, this time I don't know the quality, so I'm going to have to find the quality before I can calculate anything else. So I need to find the difference in enthalpy between a saturated liquid and vapor, and also the enthalpy of a saturated liquid. And do the same thing for entropy. because we're going to use the entropy to calculate our quality. Okay, so now that we have these numbers, we're going to use the entropy we know to calculate the quality of 0.5s. So our quality is 78% roughly. And we can then use that to find the enthalpy of 0.5s because the equation is the same. If you're wondering, like, where does this equation come from? If you forget, it's just that quality is equal to the enthalpy minus the enthalpy of a saturated liquid all over the difference. And that's the same for any property. So once you know the quality, you can just rewrite that and solve algebraically to figure out your equation. Okay, so I'm finding the 0.5s right now. This is pretending that it's isentropic. I plug it in and I get 2047.6 kilojoules per kilogram. Now, this is not actually the enthalpy. Why is it not actually the enthalpy? It's not actually the enthalpy because I don't have a perfectly isentropic turbine. So I have to correct it. So we're going to use that efficiency of that second turbine to figure this out. Problem said it was 80% efficient. So I put 0.8 right there. And I just rearranged to solve for enthalpy 5 because I knew everything else. This is enthalpy 4. That's one we calculated earlier, knowing it was a saturated vapor. I have both those values. We just calculated this one. And so I just rearranged to get that. If you're confused about that, I'll go ahead and show it to you. Make sure I'm being careful here because algebra gets all of us. So turbine times the difference at the bottom minus H4 is equal to negative H5. Okay, I don't have it, sadly. I'd have to put a negative sign on both sides, but you get the point. Okay, so we have the enthalpy for state 5 now, right here. We have the enthalpy for state 4. And so we're making good progress. So what's the next step going to be? Well, the great thing is this gives us the work by the low pressure turbine because we knew how much power it had to produce and we know how much enthalpy is dropping across the turbine, which means we can find the mass flow rate. So the work per unit mass of that low pressure turbine, the work it's producing, is simply the difference in enthalpy from state 4 to state 5. Not S's, this is just the regular numbers because the S's is our ideal isentropic case. We don't have an ideal isentropic case. So that's 593 kilojoules per kilogram. And then since I know how much power it's producing, which is 1500 kilowatts or 1500 kilojoules per second, I can then solve for my mass flow rate. I just take the power output and I divide it by the work per unit mass. And I get that I have 2.529 kilograms per second of power being produced by this low pressure turbine. Okay, so things are going pretty good here. Let's keep on taking a few more steps to figure out that final temperature and pressure and everything else that we need to know. So, issues we have. 1, we can't get state 4s, 1 or 2, because we don't have enough information on them. But maybe we can figure out something about state 3, okay? Maybe we can figure something about state 3. So let's calculate the work done by the high pressure turbine. As a note, you can actually find out state 1, it's a saturated liquid. We knew the pressure. So I was wrong to put that 1 there. But we can't find out state 2, so it doesn't really help us much there. Okay, so what's my work done by the high pressure turbine? Well, first off, I'm going to need to know what my mass flow rate is. And so I know that the mass flow rate for my low pressure turbine, but how much mass is being taken to the process heater? If I can figure that out, I can figure out how much mass flow rate is going through my high pressure turbine. The great thing was it told me a percentage. It said a certain percentage was going through my process heater. And sorry, actually said a certain mass flow was going through my process heater. My bad. And so I had 1,000 kilograms per minute. That's why I have a 60 on the bottom here. So I went ahead and turned 1 minute to 60 seconds so I could have it in the same units. And so what this tells me is that I have a total mass flow rate of 19.2 kilograms per second going through the high pressure turbine. Another thing we know is we know what the work of that high pressure turbine is. We know it's producing 5,500 kilowatts of power. And since it's producing that much, and it has this mass flow rate, I can then figure out what the drop in enthalpy is across that turbine, which comes out to be 286.5 kilojoules per kilogram. Okay, so if we know the drop in enthalpy, well, that's the difference between H3 and H4. So H3 would turn out to be 3,075.4 kilojoules per kilogram. Now that by itself is going to be enough for us to figure out the rest of this problem. Because with this enthalpy, I can then go to my superheated tables and I can figure out where I'm supposed to be. Okay. But we will need one more property. Because at HIMI, we don't actually know the temperature or the pressure going into that high pressure turbine. So let's look at point 4s right here. Let's look at point 4s and see if we can solve it. Okay. So if we knew our entropy at state 3, well, that'll be our entropy and our enthalpy. We will do interpolate and find our pressure and temperature from that. It would not be fun, but you could do it. So let's see if we can find the entropy at state 4s. If we can do that, we're going to be golden. Luckily, we can find that without too much terrible work, because now we know the enthalpy of state 3. We couldn't do this before because we didn't know this. So using that high pressure turbine efficiency, I'm able to find the enthalpy at state 4s. If I know the enthalpy at state 4s, well, guess what? I can calculate my quality. So I know what my pressure is at the end of that high pressure turbine, and I now know my entropy. I just needed one of the states. Sorry, I needed my enthalpy. I needed one property to figure out the quality. And so I just pull in all my properties like before, and this time, instead of calculating the enthalpy using my entropy, I'm calculating the entropy using my enthalpy. I can go either way. So first off, let's calculate quality. I have a 5s here. I am sorry, that's supposed to be a 4s. There we go. So I take my enthalpy for that point that we just calculated. And I know the rest, so I plug it in, I get a quality of 0.9742. Makes sense? We want to have a high quality steam leaving our turbine. And it's actually 100%, the real turbine, but either way. And now we use this quality to then calculate my entropy for that state. So the entropy at state 3, which is the same as entropy at state 4s, that imaginary ideal isotropic state, is 6.359 kilojoules per kilogram Kelvin. Okay, so with this, we have both the enthalpy and the entropy at state 3. And how do we get it? Interpolation. It's absolutely horrible. Okay, now using moving magic, I've just jumped over here. These are the superheated water tables, and I want to show you basically how you'd go about this, because doing a 2D interpolation is going to take way too long to do by hand to show that to you. So, first off, we have two values. Our enthalpy is roughly 3,000. I'm just going to pick that number for now. And our entropy is about 6.36. So I'm actually having to look through here and see when I get close to that. I look at the enthalpy column and I look at the entropy column. So first thing you're going to notice is that my entropy for these low pressures is way too high. I don't actually see it. So first off, match your entropy. Find it where you can find it. So you're looking for that like 6.36. Okay, still way too high. I'm getting closer. Still not there. Okay, so somewhere, right here. So at 2 megapascals, my pressure has to be above 2 megapascals because that's the first time I actually have the ability to do this. Okay, now we're going to look at enthalpy. Well, you see this for 6.34. Enthalpy is 2800. That's not 3000. Let's try the next one. 6 point, somewhere in between these, still not 3000. Let's go to the next one. It's somewhere between these two, not 3000. Go to the next one. It's still somewhere between these two, still not 3000. Go to the next one. I'm going to keep on doing this until I find something that's really close here. So this one is actually decently close, but it's still not 3000. It's actually 3075. So I still need to go higher. And so you're going to keep on matching it until you find a place. Like, so maybe here, let's check the next one. Well, nope, it's not right there because I need to keep on going higher. I'm getting pretty close here. Okay, so these two values, you can see that my entropy is 6.3, this is 3043 right here, and on this one right here, looks like these are probably my values. So here's the issue. You're required to find the pressure and the temperature matching it. Now, you're trying to find it for using your entropy and your enthalpy. You're having to interpolate both between temperatures and between pressures. So this is a 2D interpolation. It's not easy. How can you do it? There's lots of ways you can do it. It's just not fun. Okay, so way number one, if you're just going to try to go to a best guesstimate here, best guesstimate, is you just pick and choose. So like, for example, let me go ahead and get my writing ability on this. And screenshot, capture full page. There we go. Okay, I can draw on it, perfect. So what I'm going to do is, first off, I'm going to just say, okay, I'm just going to ignore the fact there's, this is not quite the right pressure. I'm going to choose these two values, and I can then interpolate between them to find my correct temperature. Okay? I can do that. It'll be fine. I can do the same thing over here. If I wanted to, I could take the average of those, and guess what? I'd be in the ballpark. Okay? It's somewhere between 350 and 400. In all honesty, it's 365. Okay, I can also do a similar thing to find my pressure. So I choose, once I've found my, temperature, I can then go across and do something very similar for my pressure. So I could choose, I don't know. I could interpolate my enthalpy for both of these, find out what it is at that temperature, do the same thing over here, and then interpolate between them to figure out where my pressure is. But in the end, you're going to need to do a 2D interpolation to get a really accurate result. That's way outside of what you can do by hand easily. And so I would strongly suggest you use like Excel. Excel has a 2D interpolation function. Python does. There's various little calculators online. And it'll take a little while because you're going to have to type in your values for each of these guys. And once you've done that, it will interpolate for you and tell you what your pressure and temperature is. You'll only need to know your enthalpies and your pressures and your temperatures. These would be like your x values, these will be your y values, and this is your z values when you're playing those functions. So, is it fun? Goodness, no, it is not. Is what you have to do? Yeah, sorry to say that you do. But, there you are. Other ways you could do this? Sorry, I'm just trying to think of other ways you could do it. You could make a surface plot. Like, think about this as a field, more or less. If I have 2 points going like this, and I have 2 points going like this, and I connect them, I would have a surface. And I could find where on that surface, though I definitely flipped up, would be more like this. There you go. I have a surface. And I could find where on that surface I am at 3000. So that wouldn't be too hard to do. Sorry, 3075, whatever the value of enthalpy is. So there's lots of different things you can do to try to figure this out visually, otherwise. But a 2D interpolation algorithm, just find it online. Like I Google searched it for you just to show you what you would find. So here's a place that explains it. This is why I'm not going to do it. There's too much to do here. And you can also learn how to do it in MathWorks, in MATLAB, in Excel, in Python, whatever it is. Just choose and use. Okay? Choose and use. Okay, so if you do that, and all goes well, what will you get? And you'll get the, one off. There you go. You get a pressure of 6.4 megapascals and a temperature of 365 degrees Celsius. If a teacher gives you this problem on an exam, they are evil. They are evil. By the way, there you go. So thank you all so much. I hope you have a wonderful day. And maybe one day I'll upload a by hand 2D interpolation solution just so you can see the horror of that. But that's it for now. Have a good one. Bye-bye.